For today's class, I want to introduce you to a new distribution. This is called a chi-square distribution. What we've done so far, I skip a couple of chapters in the textbook. I think it's like 11 and 12 I skip. 11 and 12 focus on a method of examining a relationship between two variables known as correlation. And there's an expression in statistics that correlation does not prove causation. Correlation is the idea that you have two variables, and depending upon how correlated they are, they tend to move together. So imagine my left hand and my right hand are interlocked. If I were to move my right hand, what would happen with my left hand? It would move with it, right? Now imagine my left hand and my right hand. If I move my right hand and they're not touching each other, what happens to my left hand? Nothing. That's zero correlation. So it's a measurement of how they move together. And we've built a whole suite of ways to measure correlation and how, like I said, two variables move together. Political science, we've gotten away from examining solely correlation. So I don't want to teach you something that, quite honestly, was outdated in the 1960s. I'm going to skip that, and I'll sort of circle back to the idea of how do we measure two variables moving together, but not really base it on correlation. So that's the next class that we'll have when we come back from Thanksgiving break. So what we've done so far in 9 and 10 is look at situations where you have a categorical independent variable like gender, and a continuous dependent variable like words read per minute or income or shoe size or number of chips in a bag of chocolate chip cookies. Like those were continuous dependent variables, and that's why we were using things like sample means. What we're going to do in this chapter, I've skipped ahead to chapter 14, is we're going to look at situations where both of the variables are categorical in nature. So you can have a categorical dependent variable and a categorical independent variable. And then next class I'll talk about situations where they're both continuous variables. All right. So that's where we're at. I've just got these last two chapters to cover. A final week of class. I'm going to do a review video. Because the Thursday of the last week of class is the study day, we're not meeting. So I'll do a review video in the Tuesday class, and then that way you can watch that as your class for that week. All right. So let's talk about this chi-square. The chi-square was developed as it's known as a non-parametric distribution. And the chi-square statistic is designed for situations where you have categories. And you're looking at the number of observations in a category. There are two ways to test that I'm going to teach you today to use the chi-square distribution. One way is what we call a goodness of fit test. So it's with a single variable, and we just want to know if what we observe and the data that we collect meets our expectations as to how that variable should be distributed. So imagine we have a situation where we want to categorize people into personality types. And there are all sorts of personality type tests out there. What's the Myers-Briggs something? There we go. Wes Fondren, the chair of comm, he's really good at that. He can like have a conversation with you and then tell you your personality type. He was trained in that. In political science, we talk about personality types, not just with individuals, but also we subscribe states a personality type and give them cultures. When I was an undergrad, I loved this paper that I read that was about the Southern subculture of violence, and it gave each Southern state a violence score. So in this example, let's imagine that we've got a bunch of students and we categorize them into these 4 categories. People who have alpha personalities. They are an extrovert, which means they like people and they're comfortable in situations with other people, and they favor norms. Norms is just a fancy word for rules. Betas are introverts, but they are also norm favoring. Introverts don't really want to be around other people. A gamma is an extrovert who questions norms. It's a rule breaker. And a delta, an introvert and norm questioning. Okay, so we have these 4 personality types. Let's not look too much into them. Let's just treat them as categories. So if we have a study that classifies individuals into these categories, it looks here like we have a fair number of alphas, a small number of betas to follow, gammas, and then deltas. What do we notice about how these variables are observed? Or how these types are observed? What's the most common type? Alpha, right? There's lots of alphas. What aren't there many of? Betas. If I were to say, all right, let's think about this in a framework of making inferences from it, what might we expect about personality types? No, but how we observe them or how they're sort of distributed. So our extroverts are our alphas and our gammas, and there are more of them, and our introverts are pretty small, betas and deltas. That's true. That's what we observe in this group. Is there any reason why we should suspect that we should get more extroverts than introverts? That's your theory. If we wanted to test that theory, what would we test it against? So if you want to test the theory that there are more extroverts than introverts, okay, if we were to test that, what would be the null hypothesis? That there are not. What would that look like? What would that look like? How many more? Not necessarily. What's one way to say that there isn't more of something? That everything is equal. Okay? So what would this look like in a null hypothesis that says you're equally likely to be anything? No, don't end the show. Our distribution would be, what's the word for that, Jeff? Flat. You just got to say it out loud so that I can hear over all these sick people coughing. Okay? All right. See, you just got to, just got to speak up. All right? What the chi-square does is it allows us to do just that. Compare what we observe to what we would expect, and to see if what we have observed is statistically significantly different. Are the frequencies observed in a sample significantly different from the frequencies we would expect? Where do these expectations come from? Well, they can come from a couple of places. They can come from our previous theory or previous research. Raise your left hand if you are in fact left-handed? 1. 1 of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's what I expected. Why did I expect, Alex, that there would only be one left-handed person in a room full of 14 people? Because left-handed people are freaks, and there's only about 10% of them in the population. You're welcome. Right? They're weird. Like, clearly the right hand is the best hand. Again, they're freaks. But the whole point is, and to prove that being right-handed is the right way to be, is what happens when you write with your left hand from left to right. Yeah, you walk around and you can identify left-handed people because they have like ink and pencil right on the heel of their hand because they smudge over what they're writing. Yeah, you got to kind of like write like this, right? That's wrong. Just write right-handed. Do it the right way. That's why we call it the right hand. Okay. Previous theory or research shows that that handedness is about 10% of the population. So if I am in a room of people, I would not expect that the room would be 50-50. That wouldn't make any sense. Or we can assume equal distributions because there should be no reason why you have one more than another. Right? Look out into the parking lot. Should we see all red cars? Should we see all blue cars? Should we maybe see a bunch of different colored cars? Right? We don't have any expectation. There's no previous research to tell us that the parking lot at Coastal Carolina is going to be filled with blank colored cars. So we have an assumption that there's an equal distribution among the categories, and that's perfectly fine. Particularly if you're testing it in like a null hypothesis framework. So here's that data from the bar chart. And what we actually have is a little O under our frequency. That's too big. It looks like a 0. It's really a little O, but my pen isn't that precise. A frequency O is the frequency that we have observed. Now before I give you the answer on the next slide, what might be the frequency that we expect for our categories? It would be an equal number. What magically would that number be? Yeah, number though, not the percentage. Wouldn't be. It'd be 147. My daughter is learning how to ballpark in her math, and 588 is about what? 600. 600 divided by 4 is about, it is 150, but I got 12 that I'm away from, so 12 divided by 4 is 3. 150 minus 3 is 147. Second grade math, kids. No? Okay. But yeah, you've got your phone, so that'll help you out. All right. So we would expect 147 in each category if our assumption is that they're equally distributed, right? There we go. But what the chi-square actually does is it focuses on this. how much difference is there in what we observe versus what we would expect. Okay. So the chi-square is going to focus on the difference between the frequency observed minus the frequency expected to see how far away we are from our expectation. So the fact that we had a couple of bars that were really high and a couple of bars that were really low. We can measure that in terms of the difference. This should sound really familiar to you. When have we done something like this before, where we've measured the difference between what is expected and what we observe? Exactly. This is exactly like that. Right? We're measuring the difference from what we expect, which in the standard deviation is the sample mean, from what we observe, which is each individual observation. Now remember, with standard deviation we had a problem, and it involved solving that problem by using a square. What was the problem? Is that when we had to square these numbers. Why? Because the sum of all the differences would be 0, which, as you can see from this one, if you just add up how much difference there is, it adds up to 0. So how do we traditionally solve this problem? How do we solve this problem of having all of our numbers cancel each other out?
Square.
Yeah, we square them, because squaring them does what? Takes away the negative sign. All right. So that's the next step in the process. This is telling us how much difference there is, and because eventually we're going to sum all of the differences, we're going to have to square it. So now we have our numbers here. We have 104 squared. We have 82 squared. So our chi-square is we should just add all these numbers up, right? No. Because we have to think about this. We have to normalize this. We have to take this number and make it applicable to this distribution that we're setting up. So when we do that, and when we did that with the z-scores and the t-scores, we sort of standardized it by dividing by something. Remember that? We divided it by the standard deviation, how much spread there was, because the spread gives us the shape of the curve. Instead of doing that, what number do you think we should control our difference by in order to standardize it? What number up there that we already have? Close. Why the expected frequency? In this example, that's correct. In this example, it's the same for all of them. But if it weren't our expectation that they'd be equal, we would want to sort of capture how much difference there is from the expected. So what we're actually going to do, again, very similar to what we've already done, is we're going to take this product and divide it by the frequency expected. So this is our chi-square. It's not an x. It's a chi. C-H-I. It's the Greek letter. Chi, and you can tell it's a chi. Why? Because it's got a squiggly to it. Chi raised to the second power, chi squared, is equal to the sum of frequency observed minus frequency expected squared divided by frequency expected. This is the simple way to notate this, to tell us what we're doing here. It could get a little bit more complicated, and it actually is when we do the next chi-square, because right now we just have one variable. But when we have two variables, then we have to start talking about rows and columns. But let's just, appreciate this for the simplicity. One of the things you have to do is you are responsible for calculating the frequency expected. And in the most instances, you can just take your n and divide it by the number of categories. Or, as they show it here, your frequency expected is your hypothesized proportion. What was our hypothesized proportion for each of the 4 categories? Represented as a number. Huh? Nope, that was the number of actual. A proportion is what? It was 1/4, right? So it was 0.25. This is how they do it in the textbook. It's your hypothesized proportion, which was 0.25, times n, the number of observations you had. Proportion is just a fancy word for a fraction, right? We expect 1/4 of the n to be the expected value. That was redundant. Okay. So that's our new statistic. It's called the chi-square. This is what it looks like. It looks normal-ish, except for what? Well, a couple of things. First, the first thing that I notice is the axis. Where does our axis start at?
Starts at 0.
Yeah, it's always going to start at 0. Why? If it starts at 0, that means it can only be what type of number? Positive. Why can't it be a negative number? Because we squared it. All right? So it's always going to be a positive number. It's going to start at 0. If we have a chi-square of 0, what does that mean? Exactly. That there was no difference between what we observed and what we expected. This is sensitive to the number of observations we have, and it's also sensitive to the number of categories we have. So the shape of the distribution is going to change depending upon how many degrees of freedom that you have. This is what the chi-square looks like with 1 degree of freedom. So you have like a handful of observations depending upon the number of categories you have. So if you have 2 categories, you have 3 observations. Right? Really small number. Right? As we increase our degrees of freedom, let's see if I can get this thing to work right. The shape changes. At 3 degrees of freedom, we kind of see the peak, right? We see the up and down part of it. 3 to 4, it starts to flatten out. 5, 6, 7, keeps flattening out. Keeps moving and moving and moving and moving. Now what's happening is it's just moving off the screen, because the scale at the bottom is not changing. So all of the space for the tail is just going out further and further and further. This is how you're going to encounter it most frequently. Lots of examples are going to have degrees of freedom somewhere between like 0 and 9. Right? So it's going to look like this a lot of the time that you encounter a chi-square. Always a positive number. And the last thing is, when you look at the shape of it, you can see that it's positively skewed. Because if we were to find a common point, use a straight edge here to go across and then down. Where is the bulk of the area in which side of the tails? In the positive side or the negative side? This being the negative side. Yeah, look at all of this. All right, there's a lot more there than this tiny sliver. It's skewed towards the positive, which makes perfect sense because it really can't be negative ever. A couple of assumptions in order to make this work. First of all, the observations have to be independent, which functionally means you can't be in multiple categories. You can't be both an alpha and a beta at the same time. You got to pick one. That's not helpful. You have to pick one. So no observation can be in more than one category. Also, we have an expectation that you're going to expect to observe all of the categories. So there's none of the expected categories should be 0. If you have a list of categories and you expect them to be one of them to be 0, what should you do? Not include it as a category. Okay? So if we were doing a survey of people's religions in this class, and I don't expect there to be any Jedis, should I include Jedi as a category? No. Right? So we have to be a little bit more judicious about which categories we do. So could I expect that there would be a Baptist in this room? South Carolina, pretty good chance. A Catholic in this room? Possible. Right? Jedis? No. Pastafarians? No. Okay? Really doubtful that there's a lot of Buddhists in here. Possible, but probably not. Okay? I expected, back to my earlier example, that with a class of 15 people, there'd be at least one person who was left-handed. And I had one. Thank God. Or else I'd look like an idiot. And I'd have to go around searching for Jedis and Pastafarians. The other thing is that we should have a sufficiently large enough sample so that if we include it as a category, it should be about at least 5. It gets really wonky when you're less than 5. It doesn't give us the best answers. And this is just a function of our sample size. So if I have a room of 15 people, I probably should not go with a list of 6 different categories, because I can't get 5 people in each of the categories. If I have a room of 15 people, I should probably stick to Judeo-Christian, other, and maybe none. Like that would be reasonable, but really probably, just a couple. I don't want to set myself up to make my chi-square not work. So doing this is known as a goodness of fit test when you have a single variable. And all we're doing is testing the difference between observed and expected. So a null hypothesis would look something like this quality is evenly distributed. Or the alternative hypothesis would be that this quality is not evenly distributed.
So we always assume null hypothesis is going to be variable.
Mm-hmm.
If it's positive, it's not going to be.
Yep. Unless you have previous research to do it, right? So again, I came in here knowing that measures of handedness in the population puts it at about 10%. So I have my previous knowledge, and I use that to update my assumptions. There's a whole field of statistics like that known as Bayes' theorem, where you should use your current knowledge to update your assumptions, and it's hard.
How do we find the different expected frequencies if the way we found it earlier was we had to use a proportion, you know what I mean?
Mm-hmm.
If we don't, if they're not going to be the same, how would you?
You'd be given that. So where did I come up with my 10% rule for left-handed people? Previous research, right? And I can do the same thing, right? I could do hair color, right? Being a ginger is a rare thing. Do you know what the percentage of people who have red hair is?
2.
Yeah, it's 0.02. So less than 2%.
Yeah.
Okay.
I know what you mean.
All right. It's rare. We have that as an assumption. We have this previous knowledge. We can build it in. This is where, again, in the setup for the null hypothesis, it says the distribution of observed frequencies fits the distribution of expected frequencies. And if I expect them to be evenly distributed, that's my expectation. But if I expect it to be 0.1, I could do this very simply. Let's say Alex wants to test the theory that left-handed people are smarter than right-handed people. Now, there's one way in which we could do that, right? We could get every person out there and collect 2 pieces of information on them, their handedness and their IQ score. And we could do it like we've done traditionally, a difference of means test. Or Alex could say, listen, we expect handedness to be about 0.10 in the population. I'm going to go to Faculty Senate, which has lots of smart people in it, and see if the proportion is what we expect versus what we observe. So go to Faculty Senate and ask every PhD in the room, what's your handedness? Now, if Alex's alternative hypothesis is that this distribution doesn't fit, what would you expect to find? Or what would you hope to find?
Strange increase in left-handed people.
Yeah. He goes to Faculty Senate and it's like 80% left-handed. Same question, different approach depending upon the data that he has available. We do the exact same process. Don't copy this down, right? It's the exact same process. You figure out what you have and what you need. One of the things that we need is degrees of freedom. And of course, that's slightly different than the way we've done it before. Set our decision rule the same way that we've done before. Alpha is going to be equal to 0.05. We calculate the statistic. Decide whether or not to reject the null hypothesis by comparing the statistic that we calculated versus the critical value, level of significance. I don't really like Kramer's D or Kramer's phi, but I'll show it to you later. So how do we do degrees of freedom? For this, we're focusing on the number of groups because that's what we're actually comparing. We're not comparing the 588 people. We're comparing the 4 groups. So if I put n up there and said the number of people, it would be dependent upon actually the number of groups. So the degrees of freedom is your number of groups minus 1, because we're calculating one statistic. One statistic from 4 groups. Leaves us with 3 degrees of freedom. We're going to take that degrees of freedom and look at our table. Chi-square is a little unique because it's not symmetrical. It's only on the positive side. So with chi-square, we actually put all of the decision rule area, right? All of that 0.05 in the tail. It's only a one-tailed test. The reason I like this printout is because it can remind you that this is a one-tailed test by showing you that the chi distribution has only one tail. Right? This part over here, that's a tail. Is this a tail? No, not a tail. Tail is the part that goes out longer. If you forget, look at it like a cat, a dog, or a squirrel or something. The tail goes out longer. Right? So we've got one tail in a chi-square, and it reminds you, right here, the shaded area is equal to your alpha for that. So which column are we going to use? The 0.05, not the 0.25, because we're not splitting it in half for 2 tails. We only have one tail. We're only going to use this column for now. So with 3 degrees of freedom, what is our critical value of chi-square? 3 degrees of freedom, 7.815. So for an alpha of 0.05 with 3 degrees of freedom, the critical value is 7.815. If our chi-square is greater than that number, we can reject the null hypothesis. Rejecting the null says that what we observed is not what we expected. I showed you that already. So how do you do it? You don't do it like this. You're going to get lost doing it like this. I do it like a table. So I have my frequency observed. My next column is my frequency expected. And then I take the equation and I break it down into the individual steps. So here's our equation. What are the individual steps? What's the first step? The parentheses. Do we have that? Step 1. So I'm going to have a column that's FO minus FE. I'll put it right next to the column that is FO, FE, FO minus FE. If you're smart, you put them in the right order. What's the next step? The next is the exponent. So I'm going to take that number and I'm going to square it. So I'm going to write down another column. FO minus FE parentheses squared. What's the next step? All right, I don't have any multiplication, but I do have division. That's step 3. FO minus FE squared slash. I'm not going to write it as a fraction. Slash FE. Otherwise, it gets really high. Just do slash FE. All right. Last step is what? This one here. However many rows I have, just put a line at the bottom and go down the column. And the bottom is your summation for that column. right? 4 steps. Easy. This makes it look messier than it has to be. What they've done here is taken this and written it out 1, 2, 3, 4 times, because we had 4 categories. No, don't do it that way. The answer to our original example was a chi-square of 166.74. What does that mean? Right? We're going to reject the null hypothesis. Why? Because we're way out here. We're way out here. What we observed does not match what we would expect. So if our expectation is that personality type is evenly distributed in the population, our sample allows us to reject that and say that personality type is not evenly distributed in the population. Now remember, I'm a statistician that says it's either significant or it's not. There's a test, not a test, there's a statistic out there known as Kramer's phi, P-H-I, not phi. That's what sororities call it. They're wrong. Phi. Some sororities do. All right, Alpha Phi at the University of Albany said it was Alpha Phi. And I'm like, no, it's phi. But I'm not going to argue with you. Phi, phi, pho, fum. No, it's phi. Kramer's phi is a way to measure the effect size. So, and when I say the effect, it's the difference amongst the groups. You take the chi-square that you have, and you divide it by n, which is the size of your sample, so 588, times the number of groups, which is 4 minus 1. You get a number that's square rooted, so it's going to be in between 0 and 1. They always end up between 0 and 1. And then they basically say, well, depending upon the value, you either have a small, medium, or large effect. Listen, I just want to know if there's an effect. I just want to know if there's a difference. This is an option. All right. So a small effect, phi is 0.10. A medium effect is 0.3. The textbook asks you to do it. If you're doing this in a paper, you should report it, because there are people out there that like these like add-on statistics. So if you ever present information, go ahead and present extra. You don't just present the mean, you present the mean with the standard deviation. Because I know what the center is, but I want to know what the spread looks like. If you present a chi-square, go ahead and present the phi. Phi, pho, fum, whatever it is. Okay? What about the situation where we have unequal expected frequencies? So maybe like our handedness example. Well, then you just apply that expected frequency when you're calculating how much of the overall sample you should have. So you see here in this version of it, when they calculated the expected, they said, well, we actually kind of know what proportion in the population these 4 types should be. So they just went ahead and applied them the expected pop proportion to the number, and they came up with different values. Right? That's all you do differently. But you got to have those numbers to begin with. and you do the same thing. That's the first version of the chi-square. You can use that when you have only one variable and you want to see if there's differences between the groups. When you have two variables, the test you want to use is the chi-square test of independence. So we're testing two variables to see if the distribution of observations within those two variables is independent or not. So to change Alex's handedness paper, give me a nominal, ordinal, or whatever, a categorical way to measure intelligence. That's not categorical. That's a number that ranges. Categories. How do you, to an employer, show them how smart you are? How did I do it to get my job? Why are you here? Yeah, why are you here? Huh?
You showed them what you got in your classes?
No, I showed them that I got a degree. Right? No high school diploma, associates, bachelor's, master's, PhD. Those are categories. Right? I have a PhD, I'm smarter than you. You have, well, you don't have anything yet. You at least have a high school diploma, right?
Something.
You got something. That's better than the people who got nothing. So those are categories. And then handedness. Do we see an equal proportion of 90% right-handed people and 10% left-handed people all throughout those categories? Here's the example they use in the book. I don't understand it. Children are presented a picture of either an angry face or a happy face. So I come up to Chase and I'm like, bam! And then I take the face away and I say, go pick out a toy. You have 3 toys to choose from, red, green, or gray. Am I sort of priming your toy selection by presenting with you a happy face or an angry face? So I show you an angry face. What color toy do you go pick out?
Green.
Why? Why is green angry?
I have no clue, I'm just the outlier.
Okay. Anybody have a theory? Which of those 3 colors is the angry color?
Red.
Okay, you fell into my trap. Which is the happy color? What is the I don't know why I'm here color?
Gray.
Right? It's the control color. Actually, we're completely wrong. We have it completely wrong. The researchers are going to tell us that the red color is the happy color. I think they're liars. But then again, I think this whole thing is stupid anyways, and we should stop testing children. But again, it's the example in the book. So here's our data. They tortured 40 kids with this. Actually, they only tortured 20 kids by showing them the angry face. The other 20 kids got a happy face and a toy. All right? And this was the distribution. Happy face kids, 15 of them picked the red toy. 2 picked the green, 3 picked the gray. The angry kids, 6 picked the red, 7 picked the gray, 7 picked the green. We're going to see, now do we observe a difference? It appears, right? It looks like the angry people are evenly distributed, 7, 6, 6, or 7, 7, 6. But 15, 2, and 3, that doesn't look so evenly distributed, right? There might be something going on there. What we've created here with the 2 variables is known as a contingency table. A contingency is you do something if something else happens, right? So we put you in the happy column if you were shown a happy face. That's the contingency. We usually, when you see this, we think of this as the independent variable, the columns as the independent variable, and the rows as the dependent variable. So showing them the face is the cause, and the toy that they pick out is the effect. The color of the toy is the effect. So this is what we've observed. What's the next step? In our chi-square. We have frequency observed. We need what? We got to figure out how to calculate the frequency expected. The way that we're going to do this is dependent upon keeping track of rows and columns. This is column 1. This is column 2. This is row 1, row 2, row 3. What cell is this first one in terms of rows and columns? This is row 1, column 1. We use this setup in other forms of math. We really use this a lot in matrix algebra. So that's why I'm feeling okay. Well, I'll just go ahead and introduce it to him here. It's a notation that to me makes sense, because you're denoting your position by the number of rows and the number of columns. What's the angry red? Row 1, column 2. The reason I say this is because how we're going to calculate our expected frequency depends upon what row and what column we're in. In order to calculate the expected, we're going to take the row total times the column total and divide that by the total number. So we're sort of calculating the proportions of that row relative, the row and the column relative to the overall number. Does that make sense? So we're not just expecting every cell to be equal. We're going to allow it to vary based upon the combination of row and column. In this case, the face that we show and the color that they pick. So if we are in cell row 2, column 2, we're going to take the total of row 2 and multiply it by the total of column 2. Does that make sense? Okay. So when you have to do that individually for each cell. When you watch the video of me doing this, it takes forever. And I can't narrate it. So I'm like, you just sit here and watch me write all these numbers in. Because I have to do it individually and then write it in and then and I don't want to keep talking because I'm just doing the same thing repeated. This is a 3x2 matrix here, so I have to do everything 6 times. So the frequency expected row times column total divided by n. You should do it this way. You shouldn't insert your expectations. That works for the goodness of fit test. It doesn't necessarily work here because we have data from two different variables. Setting alpha and the critical value is the same, but hate to do this to you. Degrees of freedom is slightly different. The degrees of freedom is the number of rows, minus 1, times the number of columns, that is minus 1. I don't really want to explain this. You're going to have it on an equation sheet. Just trust me. So somehow with 40 observations across 6 categories, you only have 2 degrees of freedom. Just trust me. Because again, it's not about the n, it's about the categories. And you have 6 categories, and you're trying to figure out the relationships in the pairs 3 ways and 6 ways. You have to reserve some of the categories in order to do that. So you have 2 degrees of freedom. A chi-square with 2 degrees of freedom, looking at your sheet, is 5991. 5991. Again, I don't like the way that they show this, because now you have 6 of these to calculate. I like just doing it across the way. But when you do it, like I do, chi-square is 8.24. Is that greater than 5.991? Yes. So we can reject the null hypothesis. What was the null hypothesis? I skipped that slide on purpose. What was the null hypothesis here? What would we be saying about these 2 variables? No relationship, okay? So the way that they describe it in the book, the 2 variables are, when you have no relationship, you are independent from each other. That's why it's a chi-square test of independence. The 2 variables have no relationship with each other. They are independent. So flashing the angry face in front of Chase should have no effect on which toy he picks out. He should just pick out the green toy because he likes green. The alternative hypothesis is testing whether there is, in fact, a relationship between the 2 things, the 2 variables. We have 8.24. That's above our cutoff of our critical value. For our alpha of 0.05, we can reject the null hypothesis. You can go ahead and do the same thing with Kramer's phi. I'm not interested in it. Let's figure out what we've got here. Our conclusion, the frequencies representing the color preferences were analyzed, blah, 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 blah. This analysis found a statistically significant relationship between the toy color chosen and the face displayed, such that the distribution of the 3 toy colors is different for infants. Oh my God, they did this to infants. For infants, shown the happy face versus the angry face. Our findings indicate that infants' preference for red changes with the context in which it's presented. In a hospitable context, happy face, red is preferred. In a hostile context, again, these are infants. Like, you're being mean to a baby. Red is not preferred. Babies, when they're happy, like red. Okay. Good to know. Yeah. All right. That's a chi-square. You use it with categorical variables, which is good because it's really hard to get a mean out of a categorical variable like religion. And what we're looking for here is whether or not it meets our expectations. And so that's where setting up our null hypothesis and our alternative hypothesis are important.